Cambridge IGCSE, February-March 2020, Paper 22, Solutions for Question 36 to 40. Question 36. The diagram shows a transformer that has an output voltage of 12 volt. How many turns of wires are in the secondary coil? So we are provided with a transformer where this part is primary and output part is called secondary. And in the question, primary voltage is given Vp, secondary voltage is also given Vs, and number of coils in primary Ns is also given, and you need to find how many number of coils are there in secondary. Ns you have to find, here it's given Np. So you can use the equation Vs by Vp is equal to Ns over Np, where we have the value of Vs, Vp and Np, and you just need to find Ns. So you can make the equation, you can rearrange the equation and you can make Ns as the subject. So you will get Ns is equal to, that is the number of turns in secondary coil, will be equal to, this Np will go to the other side of the numerator. So Vs times Np over Vp, where we have all these values at RHS. So you can simply substitute, where secondary voltage is 12 times number of turns in primary is 1000 over Vp is the primary voltage, that is also given to 140. So you need to substitute these values and you will get 50 turns. Hence the correct answer is option C. Question number 37. The diagram shows different particles moving through a magnetic field. Which particle experiences a magnetic force acting out of the plane of the paper? So here they have given the magnetic field directions and particular charge particles are moving. Both the directions are given and you need to find what will be the direction of force and in which option the direction of force is out of the plane. So here you have to use Fleming's left hand rule. So when you use Fleming's left hand rule, the first three fingers are important. So the fingers are third finger and second finger, that is index finger, and the thumb. So these are the three fingers, where the third finger represents the direction of current, in which direction the current flows, in which direction you have to point the third finger. But here one thing is very important, here the charge particles are moving. So you have to consider if it is a proton, as you know proton is a positively charged particle. So you can take the direction of proton is same as the direction of current flow. But the charged particle which is moving is electron or any negatively charged particle. Then if it is going towards right, you have to consider the flow of current or the direction of current as the opposite of the flow of electron. This is something very important because when you consider the third finger, it should point in the same direction of current. But the charged particle will be either a positive particle like proton, then the third finger you should point same direction of the direction of proton. But if the charged particle is electron, the charge of the electron is negative, so the current direction you should consider just opposite direction of the flow of electron. This is mainly due to the conventional current we consider as the opposite direction of flow of electron. So you have to look at the charge particle charge, whether it is positive or negative. Then only you will be able to decide the direction of the third finger or the middle finger. Now let's look at the second finger. Second finger or the index finger should always direct in the same direction of magnetic field. Last one is thumb. Thumb will give you the direction of force or in which direction the magnetic field will exert a force on the charged particle so that the charged particle will be moving in that direction or bending in that direction. So these are the three fingers and you should point them accordingly. But there is one important thing. All these three fingers or all the magnetic field and the force and the current direction all should be mutually perpendicular to each other. That is very important. All must be perpendicular to each other. Now let's look at the options because we need to find in which of the option the force or the thumb should point out of the plane. So let's check option A. In option A you can see the magnetic field direction is towards right and the proton is moving towards left. That means if the proton is moving towards left, you can consider the same direction as the current direction. Now in the option A, we have already the magnetic field direction which is moving towards right and the current direction which is moving towards left. So one important thing we have discussed is that the magnetic field current should be perpendicular to each other. But here you can see they are not perpendicular but they are parallel. If they are parallel, there won't be no force because that is very important. The magnetic field and the current flowing should be always perpendicular. But in this question, it is both are parallel. Even though they are in opposite direction, they are parallel to each other. So if magnetic field and current are parallel to each other, there won't be no force experience. Likewise, we can see option B. In option B, the magnetic field is moving towards right, but the electron is moving towards left. If the electron is moving towards left, you should consider the current I direction is just opposite of the electron direction. So you can see the current and magnetic field both are moving towards right. So they are again parallel to each other. If they are parallel, again you can use this rule. If they are parallel, there won't be no force in between. So the force will be 0. So option A and option B is wrong. Now let's check option C. In option C, the magnetic field direction is towards right. That means your second finger or index finger should point towards right. And the proton is moving towards, it's down of the paper. So the current and the proton direction we can consider as same. So the current is moving downwards and it should be the third or middle finger, right? Third finger. So you should point second finger towards right and the third finger towards down of the paper, and you know this is mutually perpendicular to each other, so definitely there will be a force. Now you can keep the your left hand and you can use this Fleming's left hand rule where the third finger should point downwards and the second finger should point towards right. So you can see your thumb will be automatically pointing out of the paper or out of the plane, or it will be the thumb will be pointing towards your face. So it's what even in asked in the question, the force should act out of the plane. So in option B, the force is acting out of the plane. Hence the correct answer is option C. Question 38. When Rutherford bombarded thin gold foil with alpha particles, he found that some of alpha particles were deflected through large angles. Which statement explains this deflection? So basically, the Rutherford made alpha particles to hit on the gold foil, and most of the alpha particles pass through the gold foil without any deviations, but very limited number of alpha particles after reaching this gold foil, let it be gold foil, they reflected back with a large angle. So what could be the reason? That means since alpha particles charge is positive, only particular point inside the atom there is a positively charged part, and since very less number of alpha particles are reflected, means we can understand this positively charged particles are very less, and which is almost at the center of the atom. So that was the conclusion he made. Now let's check the options. Option C says most of the atom consist of empty space. But it's not about consist of empty space. It says that he found some of the alpha particles were deflected. So from this point, why some of the alpha particles were deflected? That is only because only a very few space inside the atom there is a presence of a positive charge. Because of that the alpha particles is also positive, so they repel back. Okay, so we cannot say it's because of the empty space. Then option B, all the positive charge and most of the mass of the gold atom are concentrated in small volume. So that is the correct answer, because all positive charge and most of the mass of the gold atom are concentrated in that small volume. Then only by hitting that volume or that part the alpha particles are reflecting back, but everywhere else there is no that massive or positively charged place or volume. That's why the alpha particles are not deflecting. Most of the alpha particles are not getting affected by this positively charged space. That means it must be a very small space inside the atom. So the correct option is option B. Let's check other options also. Option C says positive charge in the gold atom is spread evenly throughout the atom. If it's spread evenly, what will happen? All the alpha particles will get reflected, because this positive charge and the alpha particle is also positive. So when they hit, they will reflect back. But that is not happening. Most of the alpha particles are moving without reflecting. Option D, all of the negative charge is concentrated at its center. That is also wrong. So, the correct answer is option B. Question 39. The diagram shows the path followed by alpha particle as they pass between two charged plates. They are deflected downwards. What happens to beta particles passing through the same plate? Here you need to know the charge of alpha particle is positive, whereas the charge of beta particle is negative. Since the charge of alpha particle is positive, they will get attracted to the negative side. Likewise, the beta particles are negative, so they will definitely attracted to the positive side. So what will happen to the beta particle? They will deflect upwards, right? The alpha particle will deflect upwards. Hence the correct answer is option C says they are deflected downwards. That is wrong. They are deflected upwards. So option B is the correct answer. Anyway, let's look at option C and D. Option C says they are not deflected at all. That is wrong, because beta particles are negatively charged. So when they are very next to the positively charged plates, they will definitely get attracted to the positively charged plate, because you know electric charges will, if it's opposite charges, they will attract. Option D, they are deflected downwards by the same amount as the alpha particle. That is also wrong. They will be deflected only upward, because upward there is positively charged and the negative betas are negative. So they will automatically go to the positive charge only. So the correct answer is only option B. Question 40. The graph shows the count rate from a radioactive source over a period of time. What is the half-life of the source? So first of all, you need to know what is half-life. So half-life is nothing but the time taken to reduce half the initial amount. So let's check what is its initial count rate. It was 2000. Then how long it will take to become its half of the initial value. That is half of 2000 is 1000. Now we have to check how long it takes to reduce from 2000 to 1000. So we have the time is given on x-axis, so you can find it's on x-axis. Let's check 2000 to 1000. So 1000 is here, 2000 is this point. Now let's check what are the corresponding time. So from 2000 to 1000, it takes 1 hour. That means 1 hour is the half-life. Because it took 1 hour to become from 2000 to 1000. So that is nothing but half-life. So the correct answer is option B. If you find this video useful, please subscribe my channel and thank you for watching my video.